Good day, everybody. Today I want to look at a special function that's defined on the interval 0, 1. Its integral is finite, integral from 0 to 1 of f. We'll do the Lebesgue measure. D lambda is less than infinity. But for every interval in 0, 1, the set of all x such that f of x is greater than c always has positive measure for every value of c. So you give me a giant number like 10 to the 100, the measure of the set of all x such that f of x is greater than 10 to the 100, that'll be positive on every interval contained in 0, 1. So first, it was posed as a question, and a colleague and I struggled to see whether it was possible or whether such a function existed, because the question was, does such a function exist? And after a lot of work, we finally came up with this. Just recently, I came across a simpler example, which I'll show as well. But first, the difficult one here. So the idea is, we'll have to enumerate the rationals. We'll do it the standard way. You make your 1/2, and then 1/3, 2/3, then go to 1/4, 3/4, then the fifths, and then so on. Just go that way. Oh, it doesn't matter. So enumerate the rationals anyway. Then for each positive integer k, make an open ball containing that, centered at that rational number, with radius, so 1 over 2 to the n, where n gets the nth rational, plus 1, and then plus k. So essentially, for each k, as k gets bigger, the open interval centered at Rn just gets cut in half. So you're going to have smaller and smaller open intervals centered at Rn. And in particular, for each k, if you increase k by 1 or any number, then of course the intervals got smaller. They're still centered at R sub n, so it'd be a subset. So the ball centered at Rn with radius this, but with a k plus 1, it's obviously contained inside here. All right, so you do that with each rational. Now, I want to take the union of, for each k, union all those balls, intervals, I guess, in R1. So, so now k is fixed, but we just union over every rational number Rn. So do that for each k, do the union over all rational numbers. Then again, since they're getting, the intervals are getting kind of cut in half, but with the same center, then a k plus 1 would be a subset of ak. Also, the measure of a sub k is going to be less than or equal to the sum of all these intervals. And each interval, well, since this is the radius, the length is twice that amount, and that cancels that plus 1. So that's why I had the plus 1 there. So when I go from radius to the full length of the interval, it'll be double the radius. So it's essentially the sum of 1 over 2 to the n plus k. And you can factor out the make it write it as a product. Anyway, so it's 1 over 2 to the k. So the measure of a sub k is equal to 1 over 2 to the k. It's kind of like the way you show the rationals. I have measure 0, but it's a little more sophisticated because we're going to do something else. Also, since each ak plus 1 is a subset of ak, then if I do the difference, ak minus ak plus 1, or what's in ak but not in ak plus 1, well, that's a measurable set, and so is its union. But what I want to see is that each x in this interval, well, it's either in A1 or it's not in A1. So it's either in A1 or A1 complement. And then if it's in A1, then it might be in every A. So then it would be in the intersection of all the A sub k's. Or it might eventually not be in some ak plus 1. Right? As those sets get smaller, eventually maybe you stop containing that x. But as long as it's in A1, then it's in one of these sets for some k, or it's in A1 complement, or it's in every k. And so these would all be pairwise disjoint. Union would be the interval 0 to 1, but I don't need that. So you define the function g sub k to be k times the characteristic equation of ak minus ak plus 1. Okay, and so you do that for each k, and fm is the sum k equals 1 to m of those gk's. Quite complicated. Then fm's increasing as m increases. You're just adding new places where the function's not 0. So fm's increasing, and we'll define its limit to be f. And if I did the integral of f, well, it would be the integral of the limit of fn, which is the limit of integral of fm, and fm's this, but you can change this integral and sum. There's a finite sum here. And then this integral, now these are all disjoint sets. The measure of ak minus ak plus 1, well, it's less than the measure of ak, but the measure of ak was less than 1 over 2 to the k. So anyway, so this integral is bounded by k over 2 to the k, and so this sum would then be sum of k over 2 to the k, and that'll be 2. So this integral is bounded by 2. If we can picture all that, right? So we've got intervals centered at every rational, and they're getting smaller. Some might be inside an overlap, but it doesn't matter. Everything was disjoint, as I said. Anyway, so, and again, repeating the disjoint. So if I start at P, so each x in AP is either in one of these or it's in all of them. So these are disjoint. So the measure of AP is the measure of this plus the measure of that. But the measure of, since the measure of AK is less than or equal to 1 over 2 to the k, the measure of this intersection would be 0. It's less than every epsilon. So the measure of AP would equal this measure here. And similarly, if you intersect this with any of the open intervals that we were thinking about, then the intersection of that with AP would equal the intersection of it with this part of AP plus the part that's in every A sub j, from j to infinity. So all the A sub j's. But that's going to have measure 0. So the measure of AP intersect this interval will equal this measure. But the measure of AP intersect a ball will either equal, so if M is bigger than P, this bounds the measure, right? The radius, you'd have a +1 for the radius. So the length of the interval is just double that, loses that +1. But if P was bigger than M, then P is your bound there. I put the P first, but so you just put whichever is bigger, P or M, add it to N. So that bounds the this measure. And so the measure of the AKs minus AK plus 1s intersect this will be the same thing, right? Because of what I have up here. So these are equal. I just found this one, so this will be the same thing. So, upshot. Given any real number, I mean, I even did it, so you could give me a negative number, but I already did. But go to the next integer bigger. Let's assume it's positive. Then set P to be the next integer positive, I should say. Then the measure of all x, such that f of x is greater than or equal to P, which is greater than C, will be this measure right here, by what I just did. Right? The measure of AP intersect this ball is positive. And since every interval will contain a rational number as an interior point, there will be an M, so that B and M is contained in that interval. This gives us the conclusion we want. So that was pretty complicated. Hard to follow. I got a simpler one. You kind of need to sit down and look at this one. Also, after I looked at the simpler one, I realized I didn't actually have to do the AK minus AK plus 1s. Actually, you could just let, rather than characteristic of AK minus AK plus 1 to work with disjoint sets, I could just have GK BK times that characteristic, and then FM still be the sum, and you're still increasing and still unbounded. You still have all the same properties if you run through the same work. So I did not need to make those sets work with disjoint sets, although that was my first instinct. So the simpler example I'll look at now, and I'm actually glad I came across it anyway, because I still sort of wondered, had doubts if I had some mistakes or something, because the problem just seemed too tough. It was like from a comprehensive PhD comp exam practice or something. Does there exist such a function? And just felt wrong, like maybe I'm missing something, and maybe there should be a way to prove there isn't. But after I saw this example, then I kind of feel like, well, they probably studied this, and then hope people will just remember this. So anyway, so similarly, we enumerate the rationals, and now for each rational, note, if you do this integral, 1 over x minus the rational, and we'll integrate from the rational to 1. It'd be an improper integral. So I've gotten all its details, but in the end, you get, this would be the value, and note that's less than or equal to 2. But there is a vertical asymptote at that rational, kind of from the right. And what we're going to do is set fk to be 1 over that function for x greater than the rational up to 1, and then 0 otherwise. So for x less than or equal to r sub k specifically. Then the integral, as I just showed, is less than or equal to 2 for all k. And, or if I divide each of these by 2 to the k, then the integral will be less than 2 over 2 to the k. And what we're going to do is set f of x to be this sum of f sub k divided by 2 to the k. So again, what we have is an increasing function. And the integral of that increasing function is going to be less than or equal to the sum of 2 over 2 to the k. And if you do that sum, I mean, that's basically 1 plus 1/2 plus 1/4, and so on, it will be 2. So it's bounded by 2, be less than 2. And so there's a vertical asymptote at every rational number, which I guess there was for my other example as well. Although I didn't think about it that way, but there would have to be actually it's a vertical asymptote when you approach on both sides of the rational. So that's kind of strange. So vertical asymptote at every rational number. In this case, just kind of from the right. And then it satisfies that condition. I actually decided to do a little more math here. So let's see. Given a rational number, any rational number in 0, 1, that's on my list, then since there's a vertical asymptote, 1 over this function, and then divided by 2 to the k, which I pulled out here, will be greater than c as you get closer and closer to r sub k. In particular, if I solve, so I kind of multiply it up, divided by the c, and then I sort of squared both sides. I have this on the left now, so this less than that squared. Now, at the rational, the function will be 0, and then to the left, it was 0, at least for f sub k, but then you're adding all the f sub k's. But anyway, I know there's a vertical asymptote on the right-hand side, so for if you just add the rational, then for x in this interval, the function will be bigger than c, right? So you give me the c first, and well, you find a rational in the interval, any rational will do, then you've got this interval where you're above c, and just to make it rigorous again, given any interval, choose a rational in that interval, and then, well, you're some distance away from the right endpoint, and then there's also this value. Take the min of those two, just in case you were closer to the right endpoint than that value. But if you take the min, regardless, if they're two positive numbers, the min will be a positive number. And so again, we would have that condition. The measure of all x in every interval such that f of x is greater than c will be greater than 0. So that's the crazy result. Obviously a little simpler for this example, and again, it's kind of funny to think about, although it was true with, I think, my first example as well. But there's a vertical asymptote at every rational number. So it's not Riemann integrable. That's where I came across this, something that's not Riemann integrable. But it will be Lebesgue integrable. All right, so I hope you enjoyed that. Something to think about as you enjoy the rest of your day.